Welcome to Math 1300 for November 24th lecture. We're doing online lecture. DBU asks professors to do one lecture a semester online, and we're using today for that lecture. It's a good week to do it. Thanksgiving week allows you a little bit of flexibility. So we're going to do a lecture today. This is driven from section 7.4, 7.5. In that range, there's some topics there about exponents, and some of this is a review of exponent stuff we've already done, but it has its own little twist in that the radical symbol, the square root symbol, or the cubic root symbol is then mixed with exponent fractions. There's a few rules that we have to know, and some of them are things like this: x to the m, x to the n. These multiply together, assuming that the number n under the power is the same. In this case, they're both x. This is x to the m plus n. And so there's a reminder of this, but that means that x to the fifth times x to the fourth is equal to x to the 5 plus 4, which is x to the 9. That's quite different than x to the m all to the power of n. In that case, we multiply. This is x to the m times n. So we have separate terms multiplying, and we add the exponent. If we have to the power of, we're going to multiply. And this is similar that if we did x to the 5 all to the fourth power would give us x to the 5 times 4, which is x to the 9. And we see this play out in several ways, but especially in the realm of fractions. And so I want to distinguish between fractions that have a power such as x to the m divided by x to the n, which is equal to x to the m minus n. So an example would be something along the lines of this, where you have x to the 7th power divided by x to the 3rd is equal to x to the 7 minus 3, which is x to the 4th, for instance, something like that. And one other thing I just mentioned as one of the rules, x to the minus n is equal to 1 over x to the n. And so if we have x to the minus 5, that's equal to 1 over x to the 5th. So these are the rules of exponents, and we have to be familiar with these. And these are rules we've already done. We've already covered this in chapter 1 even, and then we emphasized it again, even in chapter 5 when we were canceling out fractions and simplifying fractions. These rules were already in place there. Now, the wrinkle or the new feature to this is what happens when m or n are fractions. In other words, not this kind of fraction, x to the m over x to the n, but what happens if m itself is a fraction? And that's where we get some discussion about the way radicals and exponential terms that are fractional, they come into play. And so we have a situation, for instance, where we write something as a square root, and we don't think in terms of exponents, but if we have the square root of 49, this can also be written as 49 to the 1/2. And of course, this equals 7. And we should also know, like for instance, the cubic root of 27 is the same as 27 to the 1/3, and that equals 3. And so we see that these radicals are really just a convenient way of writing fractional exponent terms. Now we get back to the situation where we have x to the m times x to the n is equal to x to the m plus n. Well then, if we have a situation of x to the 1/2 times x to the 3, this is equal to x to the 1/2 plus 3. And so now we have to, now what we have to do is get a common denominator. So we get x to the 1/2 plus 6/2. And this is equal to x to the 7/2. And so that's what happens if we're multiplying these terms together. But again, just a reminder, and this is more common, especially with fractional exponents, x to the m to the n is equal to x to the m times n. Well now, if we have x to the 1/2 all to the power of 3, this is equal to x to the 1/2 times 3. And now we have multiplying fractions instead of adding them. We don't have a common denominator. We just multiply. This is x to the 3/2. And that's quite a bit different result, as you can see. In fact, let's go back now and take a look at an example that might follow this pattern. So for instance, if we had, let's go back to our example of 49. And actually, I'm going to pick a smaller number. If we did the number 16 to the power of something like 3/2, what we would do, and this is just my recommendation, is that when you have situations like this, you start with the denominator, you take the root first. And the reason for that is, see, we can rewrite this following this line here, is this is 16 to the 1/2 to the 3rd power. And 16 to the 1/2 can be rewritten as the square root of 16 to the 3rd power. And the square root of 16 is a number we know, and that's 4. That gives us 4 to the 3rd power. And now 4 to the 3rd power, you can put in your calculator, or you might happen to know that 4 times 4 is 16, times 4 is 64. And so here's an example where this rule of exponents is played out here in this way. And this is very common in the realm of exponents, where we get a combination of a numerator and a denominator, and we split the treatment of it by handling the numerator separate from the denominator, and we treat it like this. So just one more example of this would be if we had a 3rd root. So for instance, if we had, let's go back to 27, and we said it's to the 2/3. Again, I can start in the radical, and that's the cube root of 27 squared. And that is equal to 3 squared, which is 9. And so there's an example of how these radicals can be simplified. We have these exponents that have fractional terms in them, and they allow us to then simplify using this method. And so I just wanted to mention that to you. And so now I'm going to show you a couple other examples that are important in this. And so I'll give you an example that's very similar. We looked at it briefly in class on Friday, but this has to do with using the FOIL method. And we're familiar with the FOIL method. We have a situation where we have x plus 1 times x plus 2. And we use the FOIL method. First, x squared outside plus 2x, inside plus x, and then last, 2 times 1. And this gives me x squared plus 3x plus 2. So we're familiar with the FOIL method there. But this FOIL method can actually play a role in situations where we have exponents that are fractional. And so we looked at this briefly on Friday, and I just wanted to emphasize it for a minute. I'm going to do the FOIL method, but we're going to do the FOIL method with terms where these two multiplying items have fractional exponents. So for instance, I'll do a simpler one first. If we have something like this, so if we had x to the 1/2 times x to the 1/2 plus x to the minus 1/2. So we're going to distribute. We don't even have the FOIL method here. We're just going to distribute. So we have x to the 1/2 times x to the 1/2 plus x to the 1/2 times x to the minus 1/2. All right? So there's our two terms. And this is x to the 1/2 plus 1/2. And this is x to the 1/2 minus 1/2. 1/2 plus 1/2 is 1, so that's x plus x to the 1. And this is x to the 0. X to the 0 is 1. So that x to the 1/2 times x to the 1/2 plus x to the minus 1/2 simplifies to x plus 1. Now let me give you an example of a FOIL method approach here, where you can have something like the following. So we might have something like this. X to the 1/2 plus 2 times x to the 1/2 minus 2. Now that does have a bit of a feel for the difference of two squares. Let's see how it works out. So following this FOIL method approach here, we're going to use FOIL again here. X to the 1/2 times x to the 1/2. We've already seen that's x, but I'll write it out. X to the 1/2 times x to the 1/2 plus, we got the outside, or sorry, minus 2 x to the 1/2. Inside plus 2 x to the 1/2. And last is minus 4. Now, if we look real quick, we'll see that there's a minus 2 x to the 1/2 and a plus 2 x to the 1/2. Minus 2 x to the 1/2, since the exponents match, the terms match perfectly, these two things will cancel out. And here we have x to the 1/2 plus 1/2, because we can add the exponents together. We're multiplying these terms together. Minus 4. This whole thing is actually 1/2 plus 1/2 is 1. This is x to the 1, which we call 1, minus 4. So we can see here that this fairly complex FOIL turns into a very simple term, x minus 4. All right, and so that's how these work together. Now, what we're going to do now is I'm just going to work a series of these problems. We'll see how this all plays out. I'm going to work some of the problems that are from the chapter where it says at the end of each chapter it has a section called Additional Practice. And it's a great place to begin to check to see if you have a general competency of one of these chapter sections. In other words, if you can work all the problems in the extra practice section, that means you've mastered the whole section. And so it's not a bad place to start with some practice problems. You can literally work the odd problems in that additional practice problem section of every section in the book, and you would have a good test. Have I mastered this particular area? All right, so let's work through a few of these. Let's see. How about this? If we have, this is minus 27 x to the 6th, all to the power of 2/3. Now, one of the features of multiplied terms to a power is that I can separate these out into minus 27 to the 2/3 times x to the 6th to the 2/3. Now, we have a negative here, and we have a denominator that's an odd number, so we can take the cube root of minus 27. That's minus 3 to the power of 2. So I took the cube root of minus 27. That's minus 3, because minus 3 times minus 3 times minus 3 gives me minus 27. So the cube root, so that's the cube root. So minus 27 cube root is equal to minus 3. And that right there is this term there. Now we still got to square it. Now here we have, again, we can multiply, and 6 times 2 is 12. 6 times 2, so x 6 times 2/3. This is equal to x to the 12 over 3, which is x to the 4th. So we can do 6 times 2 is 12, divided by 3 is 4. That's x to the 4th. Minus 3 squared is positive 9. So this is 9x to the 4th. And I wanted to mention to you, so I told you that there'd be a hidden clue within the video. And if you email me the hidden clue within the video, you get bonus points on your next test. And in this case, the hidden clue is the color purple. I'm wearing I guess it's a purple shirt. So the clue for today is purple. That's the first clue. I'll give you a second one a little bit later. All right, so purple. Now here's a couple other problems. I just wanted to work these relatively quickly. This is number 76. 100 to the 3 halves. Well, 100 to the 3 halves is remember, do the denominator first, the square root. So this is equal to 100. This is the square root of 100 cubed. The square root of 100 is 10. This is 10 to the 3rd power, so that's 1,000. 10 times 10 times 10 is 1,000. So that's number 76. Number 80, here we have 4 over 9 to the 3 halves. And we can treat the top and the bottom distinctively. So 4 to the 3 halves divided by 9 to the 3 halves. And take the square root first. Square root of 4 is 2 to the 3rd power is 8. Square root of 4 is 2. 3rd power of 2 is 8. 2 times 2 times 2 is 8. Square root of 9 is 3. 3 to the 3rd power is 27. So that is 8 over 27. All right, and let's see, 2 more problems here. Or actually a few more problems. Let's do this one. This is number 94. Number 94 is the following. 4 to the 2/5 times 4 to the 3/5 is equal to 4 to the 2/5 plus 3/5. Again, we're multiplying the numbers together. We add the exponents, and that is equal to 4 to the 5/5, also known as 1. So that's 4. That's just 4. We get 4 back. All right? And let's see. We'll do this one. This is number 100. Then I have to erase the board for the last set. Number 100 is this problem. 7 to the 2/3 divided by 7 to the 1/2. All right, that's a little challenging. Now remember, when you have power over a power of the same term, 7 to the 2/3, 7 to the 1/2, this is 7 to the 2/3 minus 1/2. And so now we got to do a little bit of basic fractional work here. To get a common denominator, multiply that by 2 over 2, this by 3 over 3. So that's 7 to the 4 over 6 minus 3 over 6. That's 7 to the 1/6. This can also be written as a radical like that. And the radical of 7, the 6th root of 7, I don't know this number. It's going to be like 1.1 or something like that, or 1.2. But you can leave it like this, though. This is as good as it gets. Actually, either one of these would be fine. The book sometimes will say write it as an exponent, and sometimes they'll say write it as a radical, and that would be how to do that. All right, so I'm going to work just a couple more problems here. And I'm going to give you one more clue. I have my dog with me. Not my dog, it's my son's dog, my grand dog. And my grand dog's with me, and so you have to send me my grand dog's name. I'll introduce you to her momentarily. Rox, come here. Hey, where are you? Where'd you go? Oh, there you are. All right, here you go, Roxy. I want to introduce you. Come here. Oh, you're heavy. All right, everybody, this is Roxy. So the second clue is Roxy. So if you can send me R-O-X-Y is how we spell it, Roxy. All right, thank you. Okay. So now, just a couple more problems and we will be done. All right, so here are the last couple problems. Here's one. This is 108, and this is x to the 4/5 all to the power of 10. Now, we have an exponent to an exponent, so this is multiply. So this is x to the 4/5 times 10. And now we can multiply. So that gives us x to the 40 over 5, which is 40 over 5. This is x to the 8th power. That's 108. Let's see, let's do 110. Let's see, number 110 is, oh, all right. This is x to the 2/5 times x to the minus 2/5 plus x to the 3/5. All right, so we're going to distribute, right? You can see we're going to simplify this by distributing. This gives us x to the 2/5 times x to the minus 2/5 plus x to the 2/5 times x to the 3/5. All right, so there's that. So now what we need to do is multiply these out. All right, that's what we need to do. We need to multiply these out. And so x to the 2/5 times x to the minus 2/5, we have this times that, so we can add these two exponent terms. So that's 2/5 minus 2/5. And then we have this one, 2/5, 3/5. This is x to the 2/5 plus 3/5. And that's all going to equal to x to the 0 plus x to the 1. Because 2/5 minus 2/5 is 0. 2/5 plus 3/5 is 1. And this all equals x to the 0 is 1 plus x. So there's that one. And let's see, we'll do one final one here. This is number 114. This is x to the 2/3 minus x times x to the 2/3 plus x. So we have one more example here of the FOIL method. And so on the FOIL method here, we're going to do first, that's x to the 2/3 times x to the 2/3 that's first, outside, plus x times x to the 2/3 minus x to the 2/3, the inside. And then last, minus x plus x is a minus x squared. Now, again, we might notice this pattern where we have a minus and a plus of the same term, and these terms match. What will happen is we'll have x times x to the 2/3 minus x times x to the 2/3. These will actually cancel. And this will leave us with the following. X to the 2/3 plus 2/3, because we have an exponent times another term with an exponent. We can add those. And then we have minus x squared. And that all will then equal 2/3 plus 2/3 is x to the 4/3 minus x squared. And so there's the final answer we're looking for. And so there is, that's how to do these problems with the exponents. And so that's our lecture today for November the 24th. This is primarily driven around chapter 7.4, 7.5. And so, yeah, these are the kinds of tools you have to be able to use using these exponent rules. The exponent rules are in a chart back in chapter 1, and also, I think it's 1.4, and then also here in 7.4 and 5, there's charts of some of these rules. They have a whole section on them, and they look something like this. And so you can look at those and check. I will give you the rules of the exponents on the test, but if you're looking at those rules on the test, you're probably in trouble. So yeah, so don't forget to watch the video, email me the 2 words that I gave you throughout the video that are keywords or code words. If you'll do that, I'll add a few bonus points to your test number 6, which we'll take here in a week or 2. I will see you guys live on Monday, December 1st, back in the classroom. I hope you have a great Thanksgiving break. God bless you guys.